All right, so we're going to switch gears here just a little bit and give you a little bit more information about solutions, because solutions is something that we use quite a bit in the lab, especially. So it's a good thing to kind of have a background for. So far we've only worked with pure substances. Remember, we talked real briefly in the first chapter about mixtures. What is a mixture? It's a sample of matter that has two or more substances physically combined. So they're just mixed together. They're not turned into the other, they're just mixed to combine. And so obviously mixtures are probably most likely what we find. There's pure compounds, but most of the time we find mixtures. With mixtures, you can have it. So remember, with a compound, you have that constant ratio. CO2 is CO2 is CO2. But when we have a mixture, you can vary the different amounts of each substance. So the relative compositions can be very different for the same, even though you have the same substances. Like, for example, let's say I'm putting sugar in my coffee. So we certainly know that you could add no sugar, you could add a teaspoon of sugar, 2 teaspoons, a tablespoon, you could add a half a cup of sugar, and if they all dissolve, then we have different solutions at different concentrations of sugar. And similarly, when you make coffee, you can have it very strong, you can have it very weak. So mixtures can have varying amounts. And of course, each mixture then has different properties. In this example, sweetness. So the more sugar you put in, the sweeter that mixture will be. Now, the mixture that we're going to talk about right now, we have heterogeneous mixtures. They're not very useful, but a homogeneous mixture is a solution. So they're interchangeable. A homogeneous mixture can be a solution. Now, you can actually, and I think we'll talk about it later on in the semester, you can actually have solutions of different phases, but probably the most common solution that we think of is liquid, something dissolved in a liquid. So that's what we're going to talk about right now for the most part. So homogeneous mixture, a solution, is something that has uniform composition throughout the solution, and so the properties are the same throughout the solution. It doesn't mean you can't have other solutions with the same compounds that have different properties, but for that one solution, everything is consistent. You can't see differences from one part to the other. Just interestingly, if you make solutions with water, then it's called aqueous. I think that might be on the next slide. Okay, so yeah, I think so. So when we dissolve a substance in a liquid, or it could be another solid or a gas, but we're going to focus on liquid solutions. So if we dissolve a substance, it could be a liquid, it could be a gas, it could be a solid. When we dissolve it in a liquid, we call the substance that we're dissolving into it the solute. Whatever we're putting into it is the solute, and the liquid that we're putting it in is called the solvent. So in our coffee and sugar mixture, sugar is the solute and coffee is the solvent, and together they make the solution. Now we know the term concentration. So the term concentration refers to how much solute is in a certain quantity of solution. And of course, you kind of have to have both, because, if I said to you, I put a teaspoon of salt in there. Well, what did you put it in? It could be a very, very dilute solution if you put a teaspoon of salt in a swimming pool. But if you put a teaspoon of salt in a cup of water, that might be very much more concentrated. So concentrated depends both on the quantity of the solute and the quantity of the solution, or the solvent. We can in general talk about concentration, and you've heard this. So if I say, "Whoa, that coffee is really strong," that you mean is very concentrated. Or that T is so weak. We know it's not very concentrated. So, but in chemistry, we have to know much more quantitatively what that means. So we have to know exactly how much of something is in something else. And like I said earlier, when water is the solvent, which is probably most of everything we're going to do in this class, then we call that an aqueous solution, aqueous solution. All right, so let's talk about some of the different units of concentration that we can have. Probably the most useful unit that we're going to use is called molar or molarity. So the molarity is defined as the moles of solute divided in 1 liter of solution. How many moles do we have for every 1 liter? It doesn't mean we have to have a whole liter of that solution, but that ratio is how many moles to 1 liter. So that's molarity, and the symbol is a capital M. All right, so let's try an example of, this is a very straightforward calculation. We have a sample that has 0.0341 moles of iron 3 chloride, FeCl3, and we dissolve it in enough water to give us 25 milliliters of solution. So what is the molarity? So remember, let me write it over here. Molarity equals moles. How many moles you have for every liter? Well, we don't have a liter, but we can put anything in terms of liters in the denominator and moles in the numerator. So if we have, first thing we want to do is convert this to liters. So we have to divide by 1,000. 25 milliliters. There's 1,000 milliliters in a liter. That'll be 0.0250 liters. So we can take that and plug that in the denominator, and we already have the moles. So we plug that in the numerator. So 0.0341 moles for every 0.0250 liters means, if we divide that out, that means there is 1.36 moles per liter. So you could either say 1.36 molar, or you could say 1.36 moles per liter. Either one is fine. So molar or moles per liter mean the same thing. So that's pretty straightforward. So whatever the volume is, you have to convert to liters, plug that in. Now, most of the time, so that's figuring out what is the molarity. But once you have the molarity, now it's a conversion factor. It's a ratio. We know how many moles there are compared to liters. All right, so let's look at another example. In this case, well, this is another example of what is the molar concentration. So we're going to figure out the molarity. So in that last problem, we were given moles of our solute, so that was easy. This time we're given grams of our solute, so we're going to have to do some conversions. So again, what is the molarity of a solution made by dissolving 5 grams of fructose, C6H12O6, in enough water to make 100 milliliters of solution? All right, a couple of things. Remember, let's write it up here. Molarity equals moles per liter. So the first thing we have to do is convert our solute from grams to moles. We need the molecular weight. You know how to get that. So 6 times 12 plus 12 times 1 plus 6 times 16 is equal to 180. I just happen to know that, grams per mole. So 5 grams of fructose times 1 mole divided by 180 grams. Again, my grams cancel. I have 0.0278 moles of fructose, so now I know my moles. I have to also convert my milliliters to liters, so 100 milliliters, I just moved the decimal over 3 places, is 0.1 liter. Milliliters are much smaller, so a liter, so it's a portion of a liter, so it's a smaller number. So 100 milliliters divided by 1,000 gives me 0.1 liter. And finally, I can plug it into the molarity formula. So moles, 0.0278, divided by liters, 0.1, gives me the molarity, 0.278 moles. per liter, molar, 0.278 molar, or 0.278 moles per liter. Okay, it is pretty straightforward. I hope you feel like it is. All right, so like I said, now we can use molarity as a conversion factor, because if you have a molar solution, what does that mean? It tells you how many moles you have per liter. So right here, 0.5 molar means I have 0.500 moles equals 1 liter of solution. That's just my conversion factor. How many liters equals how many moles. It's just a conversion. It's a concentration, and it tells us how much is equal to each thing. So I can use that as a conversion. Sometimes it really helps if you write your units out. So it's moles per liter. So it's 0.500 moles for every 1 liter. So that's my conversion. And now whether I have to put it multiply by 0.5 or divide by 0.5 will depend on my units, which ones cancel. So here's the question. How many grams of Na2SO4 are needed? I want to make 0.350 liters or 350 milliliters. So this is what I have to do in the lab when I'm preparing to do a lab. I want a solution that's this concentration, 0.500 molar. I want 350 milliliters of it, or 0.350 liters, and I want to know, how do I make it? How much of this do I need to put in there to make it that concentration? So this time, this is my conversion factor. There's a couple of ways you can think about it. We know that molarity equals moles. I like to do volume, moles per volume. Make sure your volume's in liters. So one thing you could do is rearrange this equation, and you can say, all right, well, I know my molarity and I know my volume. So molarity times volume equals moles. Excuse me. So you could just do that. Or like I said, the other way is that you can use this as a conversion factor. So I start with what I know. I want to make 0.350 liters, and I want it to be 0.5 moles per liter, so my liters cancel. So I know that to make this solution, I have to put in 0.175 moles of Na2SO4. So I put in 0.175 moles of Na2SO4, and then I can add enough water to be a total of 0.350 liters. That doesn't tell me how many grams it is, though, because that's what, here's the problem right there, is that I don't know what that means. So now I'm going to have to convert it to grams. So that's where my molecular weight comes in. 0.175 moles. I know that Na2SO4 equals 142.1 grams per mole. I looked up the molecular weight, 2 times 23 plus 32 plus 4 times 16. I kept at least one decimal place, so that's where the 0.1 comes from. 142.1 divided by 1 mole tells me I need 24.9 grams. So if I have a container here, I'm going to put 24.9 grams of the sample, and I'm going to add enough water so that eventually I have 350 milliliters or 0.350 liters. So once I add the solute and the amount of solvent, I get my total solution. Now technically, and we're not going to worry about this, technically we're not putting in 350 milliliters of water. It's actually a total of 350 milliliters. And so I can't just add 350 mil or 0.350. I have to put the solid in there first, then add the water up to the 350 mark, and then stir it up. So the total is 0.3. So technically there's a little bit of the solid taking up some of the space, but that's a little technicality that we won't worry about until second semester chemistry. Right now we'll put, so, and just for your information, a lot of times, now this is kind of an odd volume. A lot of times if I'm making solution, I have these volumetric flasks. They kind of look like this in the lab. And you may see it or ask me sometime. They tend to be, they have a mark right here. And they come in different sizes, so they're really standard sizes, like 25 milliliters, 50 milliliters, 100 milliliters, 500 milliliters, 250 milliliters, all those standards, and probably the most common 1 liter. And so like let's say I wanted to figure this out to more of a standard volume, same thing. I would put in, if I happen to have a 0.350, I would add the solid and then add water up to the line. And that's how we usually make these solutions. But anyway, I can use this as a conversion factor. So how many moles equal how many liters, and you just need to make sure to line up your units to cancel them. The other thing, if I like using this formula better up here, that's what I did. I took the molarity times the volume to get moles, and then I converted moles to grams. So here, like I said, use 24.9 grams of Na2SO4 and then add water up to a total of 350.350 liters of solution. All right, so here's just another example. We're working with the same compound, Na2SO4. So what was that, 142.1? Whoops. So this time I'm saying how many milliliters of a 0.5 molar solution do I need to measure out to know I have 5.4 grams of Na2SO4. So this is very similar to that last problem. Again, molarity equals moles over volume, but this time I actually know the mass and I know how to convert that to moles. So I can find out how many moles of Na2SO4 this is equivalent to. So this time I'll know the moles and I know the molarity, and I'm trying to find the volume. So it's just a little bit of the same equation, but just rearranging it differently. So I could use this equation, and now be careful with your algebra. You're going to have to multiply both sides by volume to get rid of that. And then to solve for volume, you've got to divide both sides by molarity. So moles divided by molarity. So we could take the moles divided by the molarity to get the volume, or like I said, it's the same difference. We can use this as our conversion factor. So I know that 0.500 moles equals 1 liter. So either one, they're going to work the same way. So let's start with what we know. I want to know how much of this I need to get this. So 5.40 is my starting point. I mean, like I said, I have to convert that to moles because this is in terms of moles. So I first use my molecular weight, and so I know 5.4 grams is 0.0380 moles. And like I said, I can either plug in the moles and the molarity here, 0.0380 divided by 0.5, or I can use my conversion factor, and it's basically the same thing. So 0.0380 moles. I know it's 0.5 moles for every liter, so I'm converting to liters. That's my answer. If I asked for volume and I didn't care what the unit was, this would be a perfectly fine answer, but I happened to see that this question said how many milliliters should I measure. So I have to convert this to milliliters, 76 milliliters. 0.076 liters or 76 milliliters. So again, I've got my molarity equals moles over volume, and I can either solve this equation or I can use this as my conversion factor to figure out one or the other. So if I measure out 76 milliliters, I will be adding 5.40 grams. Another thing that is really nice with solutions, and you've experienced this in your everyday life too, is that we can, so we saw just a minute ago, one way that you can make a solution is to weigh out the solid and put it in something and add water and make a solution. Well, we can also take something that's more concentrated and add water to it and dilute it down. So that's another really common way of making solutions or working with solutions. So y'all know what a dilution is, of course. So if you look at this picture, this has a certain mass of copper nitrate. with a little bit of water. This one has actually the same mass of copper nitrate, but a little more water has been added, so we know that's been diluted a little more, and you can even see it that it's a little bit lighter color. So it's the same, the concentrations are different because the volumes are different. This is more concentrated and the right is more dilute. So a lot of times what we do is we have concentrated stock solutions already made up, and then we can take some of it and dilute it down to get the concentration that we need. So let's look at that real quick. Molarity and volume are inversely proportional, so that makes sense. If you've got a small volume of a very concentrated thing, molarity will be high, volume will be low. If you add a lot of water, what happens? Your volume goes up and your concentration, molarity, goes down. So that means they're inversely proportional. So if we add water to something, it becomes less concentrated. We can use this relationship to make dilutions. So let's look at that relationship. M1 times V1 equals M2 times V2, where 1s mean the initial and 2 means the final. Sometimes you'll see M initial, V initial equals M final, V final. Doesn't matter, 1s and 2s. Now, how did I get this equation? Well, remember on that last slide, we said molarity equals moles per volume. If I multiply both sides by volume, I get M times V equals moles. And when we're doing a dilution, we're not changing how many moles. We're putting a certain amount of substance in there, solute in there, and then all we're doing is changing the volume by adding water. So the amount of moles never changes. So if initially I have, let's say I have 5 moles of something, and I know the volume and the concentration, then I change the volume by adding more water, the amount of moles doesn't change, and so my volume will go up and my concentration will come down. So that's why we can say the moles don't change. So M1 times V1 equals M2 times V2. So this is a helpful equation, a dilution equation. Notice this note down here, other units of concentration can be used in place of molarity. So we haven't talked about any other concentrations, but we will in a little while if you know percent, mass percent or something like that. It doesn't have to be molarity, but it works the same way because the more water you put in, the more dilute it becomes. So adding more water increases the volume, decreases the concentration. So how many milliliters of a 3 molar H2SO4 solution are needed to make 450 milliliters of a 0.1 molar solution? So one thing I want you to be careful about are the units. Because technically speaking, volume should always be in liters because molarity is moles per liter. However, if you're working with molarity, you have to have liters. Now, because you have 2 volumes and 2 molarities, the units will end up canceling. So your volumes can actually be in any unit as long as they are the same unit. If it makes you feel better, you can convert everything to liters, but you don't have to. So in this case, because one of my volumes is given in milliliters, I can use it, and then my other volume will also be in milliliters. If you're given a problem where you're given milliliters and liters, you need to convert from one to the at least they both have to be the same units. It doesn't matter which one, but they have to be the same. So here's my equation. So let's see what I have. How many milliliters of now technically we have initial and final or 1s and 2s. It doesn't really matter. But what does matter is that you get the correct ones to go together. So I don't care if this happens, if I call this initial and this final, or if I call this initial and this final. It doesn't matter as long as I get the correct concentration and volume on the same side together. So one of the little tricks is to look for the word of. So how many milliliters of, so this is going to be V2 in M2, or it could be V1 and M1, I don't care. And now here of So here's my V1 and M1. So look for the word of that links them together. So I have my, now someone else might come along and say V2 over here and M2. It doesn't matter as long as you get the two correctly together. So the question is, how many milliliters of a 3 molar solution do I need to make 450 mil? Here's my final solution that I want to make, 450 milliliters of a 0.1 molar solution. I might call these ones and these twos. Again, it doesn't matter. Since this is what I'm trying to make, this is what I'm starting with, and this is what I'm trying to make. Maybe these ones and twos are finals and initial. And anyway, it doesn't matter. What am I solving for? I know my, I don't know my initial volume. I do know my initial concentration. I know my final volume and my final concentration. You can rearrange the equation like this if you want to beforehand. I tend to just plug it in the way it is. So my initial concentration is 3.0 molar, and my initial volume is what I'm looking for. My final volume is, or my final molarity is 0.1 molar, and my final volume is 450 milliliters. I kind of tend to do my math and then do my last explanation. So this would be 3.0 times V equals 450 times 0.1 is 45. And now my V, if I divide both sides by 3, V equals 15. Remember, it's the same units that I have over here. So if I take 15 milliliters of a 3 molar solution and I dilute it to 450 milliliters total, the new concentration. And does that make sense? I'm starting out with something concentrated, a small amount of something concentrated. I'm adding a lot more water. It becomes more dilute. So that should make sense. So I need to take 15 milliliters. You can take this a step farther. I could say, how much water do I need to add? Well, if I have a total of 450 milliliters, and I'm starting with 15 milliliters of my initial, that means I have to add 435 milliliters of water. I kind of wrote all over this screen here. I think I have my PowerPoint coming. Let's see what happens. Yep, so you can kind of read in here. The initial molarity is 3.0. The final molarity is 0.1. My final volume is 450 milliliters or 0.45 liters. It doesn't matter which one you use. I'm sorry, I wrote all over this. 0.1 molar. Let me see if I can erase it. Yeah, let's do this. There we go. Now that I've shown you all that, you can look at the slide. Okay, so I have I've added the 0.1 times 0.40 divided by 3 gives me, I've rearranged it here. So either way, if you want to just plug the numbers in and solve at the end, or if you want to rearrange, it depends on how good at algebra you are. If you're not so good, put everything in and get it down to something simple. So I got 0.015 liters here. Here I converted this to liters, and so my answer is in liters. The question asks for milliliters, so 15 milliliters is my answer. Like I showed you, actually, if you just kept 0.1 times 450 milliliters divided by 3.0, then I get 15 milliliters. I don't have to convert. But that's how you use a dilution problem. So again, the main thing is making sure, if I had called this twos and ones, it wouldn't have mattered as long as you have the same two, the two that go together on the same side. So that's a dilution. That's a dilution. Oh, and you can see here my units cancel. And so, all right, let's look at another example. 10 mils of 10 molar stock solution of NaOH is diluted to 250 mils. What will the new concentration be? So again, now I've kind of got it a little bit different. I've got my initial volume. I've got my initial concentration, and again, look for of. I want to make my final volume, and I want to know what is my final concentration. What will the new concentration be? So again, I've got MIVI equals MFVF. I'm going to go ahead and plug it in. I think I did it the other way. I resolved it, but let's go ahead and do it before we do the PowerPoint. So I've got, and again, I can change that to liters, but since they're both milliliters already, I'm just going to leave it in milliliters. So my initial molarity is 10. My initial volume is 10. My final concentration, I don't know, that's what I'm looking for, and my final volume is 250. So I've got 100 equals 250 times M, divide both sides by 250, and then M will equal 100 divided by 250 gives me 0.4. I'm going to keep 2 sig figs. I have 2 here. Actually, I have 3 here. 3 here, but let's keep 2 since I only have 2 here. 0.40 molar. Take a minute and see if it makes sense. If I have something that's 10 molar and I have a small amount of it, I'm diluting it with a lot of water. I'm adding 240 milliliters of water. It should definitely, the concentration should go down. So it should, the number should make sense to you, and then you know you've done it right. So again, I've already shown you all this. My initial concentrate, here I converted to liters, so it doesn't matter. If you're worried about converting it, just don't if they're the same. Only have to convert it if they're different, but it's fine if you do convert it, if that worries you. All right, so my final concentration is 10 times 10 divided by 250, or 0.01 times 10 divided by 0.25, you get the same answer, 0.40 molar. Just a couple others. I am really not going to focus on these, maybe at least not till second semester, but molarity is a very useful unit in chemistry, but other units of concentration are used, and probably like in healthcare, we often use mass percent or mass per volume percent. And so I just want to introduce those to you because they are other units that are very helpful. So mass percent of a solution. And again, the reason why we use molarity so much in chemistry is because so much of, and you'll see when we get to the next chapter, that so much of our reaction calculations have to do with moles. And so molarity is a very helpful tool because you already have everything in moles. Mass is not as helpful in chemistry because you always have to convert anyway. But in a lot of other situations, mass percent is a really helpful thing. And so what is mass percent? And everybody should understand mass, or percentages anyway. We know percent is just part out of the whole. So a mass percent then is the mass of the solute component. Let's just say solute. The mass of the solute divided by the total mass of solution times 100%. So remember, molarity is moles of solute divided by liters of solution. So we're just changing the units that we're using. Here, in this case, they're both mass. I think probably one of the most helpful tips about this is if you're given a mass percent, remember what that means. So 7.4%, what does that mean? That means that for every 100 grams of solution, I have 7.4 grams of my solute. So it's kind of gives you a conversion factor already, we know. So another way, another way to say it is for every 100 grams of solution, we have 7.4 grams of NaOCl. And then that means you can subtract, since everything's in grams, you can subtract. You can't subtract volume and mass, but you can subtract mass and mass. So if I have 100 grams of solution and 7.4 grams is NaOCl, then I know the 92.6 grams is water. So that's very helpful. And actually, and I'm not going to ask you to do it, at least not right now, you could convert from a mass percent to a molarity, because if you know how many grams of solute you have, you could convert that to moles. The only problem is we would have to know the density of this to convert it to volume. So it's not as helpful. We'd have to know density. And sometimes we do know it, and so we can do it. But at this point, I just want you to understand what this means. So a mass, percent by mass, is the mass of the solute. Mass solute divided by the mass of the solution, which, remember, is the total mass, the total. So if you're given a percent, you could just say out of every 100 grams of solution, 7.4 is, so if it's a mass percent. So here again, mass percent, grams of solute divided by grams of solution. So let's just do another example. What is the mass percent of glucose in a solution if we dissolve 163 grams of glucose in 850 grams of water? What I want you to be careful about is the definition. So what's our solute, what's our solvent, and what's our solution? So we're dissolving glucose, so that is our solute. We're dissolving it in water, that's our solvent. So what's the mass of our solution? Well, we're putting these together, so actually our solution has to equal 163 plus 850. It's 1,013 grams. So our solution is 1,013. So be really careful. Just make sure you pull out everything. So what's the mass percent of this solution? Well, the grams of the solute, 163, divided by the total grams of solution, 1,013. So that's 16%. Don't forget that part. That part. Add the solution in. So that's a mass percent. And again, like I showed you on the last one, now what is it? We didn't actually have 100 grams and whatever. We had lots of different amounts, but now that we know this percent, we know that if we have 100 grams of solution, it's just a ratio. 16.1 grams is solute for every 100 grams of solution. So just keep that in mind. That's very helpful. Another well, here's another example, one more example. How would you prepare 750 grams of an aqueous solution? So that's our total. This is how much we want total, 750 grams of our solution. That is 2.5% NaOH by mass. So again, what does that mean? 2.5 grams of NaOH equals 100 grams of solution. That's kind of like a conversion factor. I know I have 2.5 grams of NaOH for every 100 grams of solution. So if I want 750 grams of solution, I know I need 2.5 grams for every 100 grams of solution. There's my conversion factor. And so I have to put in 19 grams of NaOH. 19 grams of NaOH, and then see if it's on there. Oops, percent composition. And then if we want our total to be 750, we have to add 731 grams of water. So that's just a different, that's probably a more useful in your everyday life kind of concentration. So we're going to mix 19 grams of NaOH with 731 grams of water. We will have a total of 750 grams, and our mass percent will be 2.5%. Another really useful concentration is mass per volume. Sometimes you'll see it written like this, mass per volume, like here. And it's just what it says. It's the ratio of solutes mass, that should be apostrophe, solutes mass, to the solution volume expressed as a percentage. So if you see something like this, 0.9% mass per volume, what does that mean? It means you have 0.9 grams of the solute for every 100 milliliters. So that's only the difference. Whereas the mass per mass percent means 100 grams of solution. Here we have 100 milliliters. So that's just a slight difference. So specific units can vary depending on the solution. Interestingly, physiological saline, if you were to go in the hospital, you would see that it's 0.9% mass per volume. Glucose would be a different percentage because glucose weighs different than sodium chloride. And when we get to it in the second semester, they're actually the same concentration in terms of moles. So I think it's 5.5% glucose. I can't remember exactly, but it's interesting because their masses are so different. Their mole concentration are the same, and we'll talk about that then. That's a long way off, but anyway, just notice that volume then is 100 mil. So 0.9% means 0.9 grams per 100 milliliters. So let's just do a quick example with this one. We're not going to get really complicated, but I want you to remember what the different things mean. So in this case, 140 ml tube of toothpaste contains 0.30%. Again, mass per volume, make sure you look for that. If it was mass per mass, then we'd see that. Mass per volume. So again, what does that mean? That means there's 0.30 grams for every 100 milliliters. It's just different units depending on the problem, but that's what that means. So the question is of sodium fluoride, in this case, sodium fluoride. What is the mass of sodium fluoride in the whole tube? Okay, so we know, and actually there's two ways you can do that. It's a ratio. We know that it's 0.3 grams per 100 milliliters. So now the question is, how many grams are in 140 milliliters? So the best way to do that is to take here's our definition, 0.30 grams per 100 mils. And so we can take that ratio and multiply it by 140 milliliters of toothpaste. The milliliters will cancel, and we'll have 0.42 grams of NaF. Another way you can do it, if you like this better, I don't want to confuse people, but if we know it's 0.3 grams per 100 mils, the question is how many grams is there for 140 mils? It's basically the same setup, but you can cross multiply, so it's 0.3 times 140 divided by 100 will give you X, and you'll get the same answer. It's just a different way of looking at the problem. I just wanted to mention these other units, which we won't be using in this class very much, but sometimes you hear about them out when you're reading things. Very low solute concentrations are sometimes expressed using very small units. There's a part per million unit, ppm, which is just what it says. It's how many parts per 1 million total parts. So just like percent is 1 out of 100, parts per million is 1 out of a million. Parts per billion then is 1 out of a billion. So this again represents very small numbers, which oftentimes when we're talking environmental or trace things, we have to use these values. You know, we don't want to use really tiny numbers, so we express them as parts per million. So parts per million is the mass of the solute divided by the mass of a solution, and then multiply by 10 to the 6, multiply by a million, so that you can use bigger numbers. And but again, parts per million means how many parts do you have per million parts. Parts per billion then is mass of solute divided by mass of solution times 10 to the 9th, or a billion. Okay, so what should you be able to do after you're done with this chapter? You should be able to calculate the formula mass or the molecular mass from any formula for either covalent or ionic. Of course, if it's covalent, it's usually called a molecule. So molecular mass or formula mass, either ionic or covalent, and that's just adding up the atomic masses for everything in that compound. Define the amount of unit of mole and relate to Avogadro's number. So we know that the mass, the molecular mass of any molecule, or the molar mass of any molecule, equals 6.022 times 10 to the 23rd molecules equals 1 mole. So again, explain the relationships between mass moles and number of atoms. So the atomic mass equals 1 mole equals 6.022 times 10 to the 23rd atoms, or the molecular mass equals 1 mole equals 6.022 times 10 to the 23rd molecule. So be able to do calculations like we did earlier. Calculate the percent composition if you know the molecular formula, or more likely, determine the empirical formula if you know the percent composition. Determine the molecular formula if you know the empirical formula and the molecular weight. Describe fundamental properties of solutions. What is the solute? What is the solvent? What do you do? What is the solution? Calculate solution concentrations using molarity. Perform dilution calculations. I just wanted to point out here, remember I said that it doesn't matter. Let me keep going. Define the concentration units of mass percentage, mass to volume percentage, parts per million and parts per billion. Be able to do very simple problems like we did just a minute ago. We didn't do volume to volume. It's in the book, but we didn't do volume to volume, but we did mass to mass and mass to volume. I did want to remind you, point out, to perform dilution calculations, we mostly did it with molarity. M1V1 equals M2V2. But I just wanted to point out it doesn't matter. You can use this same formula for any concentration or whatever units you want. So sometimes you'll see C1V1 equals C2V2, where this just means concentration and volume, concentration and volume. So as long as the two concentrations are the same concentration, and as long as your volumes are in the same units, you can use this equation. So, if you use the mass per volume percentage as the concentration, then this dilution problem will work just the same. If you use parts per million or parts per billion or whatever, the dilution will always work the same. Be also able to perform computations relating a solution's concentration and its components' volumes and or masses along these units. So basically be able to do the compositions that I've given you examples of. Be able to find the mass volume percent or use the mass volume percent. Be able to find the mass to mass percent or use the mass to mass percent. Be able to just know the definition for parts per million, parts per billion, and then also molarity, be able to do molarity concentration calculations. So that's it. Good luck.